Hello everyone. We will be continuing with the chapter Gaseous States and Thermodynamics. In the previous lecture, we have discussed what is a process, what are the various kinds of processes, and we had discussed few of them. We began with isothermal process. What is it? And we discussed the two scenarios possible in it. Say the gas is expanding in the isothermal condition, or it is contracting or compressing. The second process we did was adiabatic process. We tried to analyze that in the similar manner. Now we will carry on with this. We will discuss some other types of processes and discuss what are the work done and the various other parameters in that kind of processes. Okay, let's begin with it. So the third type of process we are dealing with today is isochoric process. Okay, so isochoric, as you know, is nothing but the process in which volume of the system remains same. Volume of the piston, cylinder arrangement, remains same. So basically, we mean to say that the system has volume is equal to constant. And as we know that our system follows the ideal gas equation, which says that PV is equal to nRT, and if V is constant, we get P is proportional to temperature. So as you raise the pressure in this system, the temperature of the gas increases, and if you decrease the pressure, the temperature decreases, because all other constants are positive, and R and V are obviously positive. So let's see it in the form of the piston cylinder arrangement. So the container would be something like this. So in this scenario, basically we are keeping the piston fixed. Okay, so this is basically fixed over here. We are not letting it move in any of the conditions. And then we are trying to either apply more pressure, that is in the sense we are applying more weight over this piston, or we can say we are increasing the temperature of the gas. Either of these we are dealing with. Okay. So basically one thing is for sure, that as dV is 0, we can say that dW is P into dV. That is 0. So net work done in this process would always be 0. Okay. So there are two things that can happen in this scenario. As the volume is not changing, either the gas would get heated up, okay. So in that case, what you are doing basically heat is supplied from the outside. That means delta Q is equal to delta U plus W. This is obviously 0, which says that delta Q is equals to delta U for a isochoric process. And as we know, if delta Q is positive, delta V is also positive, which is nothing but something proportional to delta T. So the temperature would increase. So we can say that in the case of isochoric process, if heat is applied to the system, the temperature of the system increases. Okay. And the second scenario that can appear is basically you are taking heat out of the system. In that scenario as well, the work would obviously be 0 itself. And as we know, delta Q is equal to delta U plus W, which is the first law of thermodynamics. this term being equal to 0 again gives us delta Q is equal to delta U, and here as the heat is being taken out of the system, this would be negative value, which instead gives us delta U as negative, which is nothing times something times delta T, which tells us that the value for delta T is negative. That is to say that the temperature of the system falls. So basically, if heat is applied to the system, the temperature raises. If heat is taken out of the system in this process, the temperature of the system goes down. Okay. Now let's try to represent these in terms of our PV diagram. So one thing is for sure, if the volume is constant, say over here, it would be a line parallel to the y-axis. Okay. So like these, if we are expanding, not expanding, if we are supplying heat from the outside, the temperature rises. Okay. So as we can say that PV is equal to nRT for higher temperature, there is higher pressure, right? So we can say that let these initial point be P1 V1 and this be P2 V2, right? And this would be P3 V3. Sorry, this volume would be obviously same. So P3 V2 and P4 V2, right? So we can say that as P1 is less than P2, so T1 is also less than T2. Thus, heat was supplied. So for the first process says that it is a heat is supplied to the system. Then only this isochoric process took place. So the pressure increased and as well as the temperature increased. Whereas P3 is greater than P4. So we can say that T3 is also greater than T4. Thus, heat was taken out of the system. When we move from point 3 to point 4. So this is a downward process. Okay, so this is basically isochoric heating, isochoric cooling. Okay, so these are the two possible cases in the case of isochoric process. That is simply just by keeping the volume constant. The property in the isochoric process is the volume is constant. Okay. Now the fourth process that we will be studying is basically in all these processes we are trying to keep some quantity constant, and under that condition we are trying to examine the states and the various processes, various happenings in the system. First we tried to look at the isothermal process, that was keeping the temperature constant. Then we tried to look at the adiabatic process, in which we tried to keep the total energy of the system constant. Then we tried the isochoric process, in which the volume was constant, and the remaining parameter that could be constant is isobaric process, in which the pressure is constant. Process under the constraint that P is constant. Okay, so in this case, as we know the ideal gas equation, PV is equal to nRT. If pressure is constant, nR is also constant, V is proportional to T. So basically under the isobaric process, the ideal gas follows the Charles law. Their volume is proportional to the temperature. Okay, so in this case, let's try to find out the work done. Work done is nothing but P into dV, as pressure is, and the total work is given by integral of dW, which is integral of P dV. As P is constant, we can take it out, So integral P dV, which gives us P into V2 minus V1, which is nothing but PV2 minus PV1, which is can be written by the ideal gas equation as nRT2 minus nRT1. So the work done in the isobaric process is given by nR into delta T. So the work is dependent on the change in the temperature. Okay. Now we can use the first law of thermodynamics, stating that delta Q is equal to delta U plus W. In this case, all the terms here are dependent on the temperature, right? We can say that this is directly proportional to temperature. Work has also come out to be directly proportional to delta T. And delta Q is obviously the addition, so it would be nothing but nR plus K into delta T. So we can say that in this isobaric process, all the three quantities delta Q, delta U and work have the same sign. If the temperature increases, they all have the positive sign. When the temperature decreases, they all have the negative sign. Okay. So let's try to formulate the two type of internal type of expansion, or as under the constant pressure condition, the gas could either expand or it could either compress. Okay. So it gives rise to two cases. Basically the first one is the isobaric expansion. So in this case, the pressure is allowed to be constant and the gas tries to expand. So it is the cylinder piston arrangement. Here, let's suppose a constant weight has been put up on the piston. So which implies that there is a constant weight applied on the piston. So the pressure applied on the system is constant. Then the gas is either expanding or contracting. Then we are saying what's the effect on the various parameters. Okay. So we can say that in the case of expansion, the delta V is basically positive, right? So what we had was work was nothing but P into delta V, that is P into V2 minus V1, PV2. So nR delta T. So as delta V is positive, P is also positive, so work is positive. So being work being positive implies that there is delta T is positive, which says that when the gas expands, under constant pressure, the temperature of the gas raises. Resulting in delta Q, delta U and work all being positive. That we saw just before we were discussing this, because delta work done was nothing but nR delta T, and delta U is directly proportional to the change in temperature, where K is a constant value, constant positive value. So we can say that delta Q would be also proportional to delta T, which instead says that if delta T is positive, all the three terms are positive. If the delta T is negative, all the three terms are negative. Okay. So the second case that arises is of isobaric compression. In this case, if heat is added to the system, heat is taken out of the system, we have delta Q as negative. So as we saw that it is directly proportional in this case to the delta T, we can say that the delta T is negative. So basically the temperature of the gas falls. And as V is directly proportional to temperature, so volume decreases. Right? So basically we are saying that if we supply heat to the system, the gas will expand. If we take out the heat from the system, the gas will compress. Okay. So in this case, delta Q, delta V and W would be negative. So the basic conclusion over here was that heat given to the system leads to expansion. Heat taken out of the system lead to compression. And let's try to represent this in the form of PV curves. Okay. So the PV curve for the first one would be, we are giving in the heat, right? And the volume is increasing. And the pressure is constant. So if the pressure is constant, this graph would be obviously parallel to the x-axis. And as the gas is expanding, so the volume is going on the right hand side. So let's suppose this was the first condition and this is the final condition. And the work done would be given by the graph under this line. So this is a isobaric expansion process from P, V1 to P, V2. Right? Similarly, the compression process would be nothing but something like this. PV curve starting from a higher volume V1 to a smaller volume V2 under constant pressure. That is a line parallel to the x-axis. And the work done would be obviously negative, given by the area under the curve of this straight line. Okay. So these were the basic 4 types of processes that take place. Okay, that we are going to be studying. So let's try and formulate the required work done and the change in heat that is required to do the processes. Right? So first of all, you should know that delta U is the change in the internal energy. Right? As we discussed in the case of isochoric process, that work is basically equals to 0. If you are trying to take a gas from a specific condition to another condition under the isochoric process, the work done is obviously equals to 0. So in that case, delta U is equals to delta Q. Right? And as we know, under that process, the delta Q supplied is nothing but NCV delta T. So NCV delta T is basically delta U. And this is in the case of isochoric process. But we know that delta U is nothing but a state process. Right? So if we try and take this gas from the initial state to the final state through any process, the change in the delta U would be nothing but NCV delta T. So this gives us a formula for the value of delta U, that is NCV delta T. From whichever process you try to take it from the initial to the final state, you have to just think about the change in the temperature and NCV. And as we know, the value of CV is nothing but NR upon gamma minus 1 into delta T, as we have learned in the previous lecture. So the value of delta U is nothing but NR delta T upon gamma minus 1. Now using this information, let's try to find the work and the delta Q for a isothermal process. Okay. So for a isothermal process, we had work TW as PdV, and we know that the temperature is constant, so PV is also constant, that is equal to nRT. So we can express this volume in the terms of pressure and temperature, right? Or we can express the volume or the pressure in the terms of temperature and volume, like this. Using this representation, we can find the integral of TW to find the total work done from one state to another in a isothermal process. So let's substitute the value from here in this equation, right? So what we get is work is nothing but the integral of nRT upon V into dV. So as we know, the integral of this portion dx upon x is log x. So what we get is nRT into log V2 upon V1. So this is the work done in a isothermal process. Isothermal work done from taking gas from V1 to V2. Isothermally, a gas is taken from a volume V1 to V2. This is the amount of work done. We have used just the ideal gas equation and tried to evaluate the integral, that is PdV. Integral of PdV. Now we knew that PV is equal to constant, so we tried to implant its value from the ideal gas equation in this formula and try to find the value. Right? We can find the delta Q as well for the process, which is nothing but delta U plus W, which can be now put as nR delta T upon gamma minus 1 plus work. And as we know, delta T for this process is 0, so this terms get equal to 0. So delta Q is nothing but work only, so which gives us nR T log V1 V2 upon V1. Please be careful that here the log is to the base e, right, not to the base 10. So if you have to put this value in terms of log 10, so you can multiply by 2.303 nR T into log to the base 10 V2 upon V1. So here work and Q are same. Let's try to do this for the second process we learned, that was adiabatic process. In the adiabatic process, what we had was PV raised to power gamma was constant, right? And we know that it follows PV is equal to nRT as well, because we are dealing with ideal gases. So we can split this PV. Let's suppose it was equal to some constant K. Let's try to split it. We write it PV into V raised to power gamma minus 1 is equal to K. That is nRT. We substitute these values. V raised to power gamma minus 1 is equal to K. Alright. Now let's try to find out the work done. Work done was nothing but P into dV integral. We have to somehow try to solve this question, because in this question the pressure is also varying and the volume is also varying, right? You have to try to find out the relation such that they both can be incompensated. From the PV is equal to nRT, and using this equation, what we have as V raised to power gamma minus 1 is K upon nRT. Alright. So we can say that, or we could have done it in a similar manner like this. dP. Yeah. Rather than formulating it like this, there is a very easy method you could have done like this, was delta Q is nothing but delta U plus work. We know that delta Q for a adiabatic process is 0 because we are not supplying any heat from outside or taking from the system. So delta Q is 0. And so basically delta U is nothing but minus work. And we know that delta U is a state process, which is nothing but nR delta T upon gamma minus 1. So we directly get that the work is the negative of it, nR delta T upon gamma minus 1. Or we can say that it is P into V2 minus P into V1, P2 V2, P1 V1, which gives us nR delta T upon gamma minus 1, the whole negative of it. So rather than finding by the complex equation PV integration, we can directly use the first law of thermodynamics to say that for adiabatic process, we have work as the negative of delta U, which is minus of nR delta T upon gamma minus 1, and the delta Q is 0, right? So this was a simple derivation. Now let's try and do with the third process we learned, that is isochoric process. In the isochoric process, we know that dV is 0, so work is obviously equals to 0. So the total heat supplied is nothing but delta U, and as we know that delta U is nothing but NCV delta T, or we can write nR delta T upon gamma minus 1. So delta Q is nothing but nR delta T by gamma minus 1. So this was pretty straightforward. Now let's try and do the last process we did right now, was isobaric process. For the isobaric process, we know that the delta work is given by P dV integral, and the pressure is constant, so we can take it out. Integral dV is nothing but P into V2 minus V1, which is nothing but nR delta T. And delta U, as we know, is nR delta T upon gamma minus 1. So delta Q is delta U plus work, which is NCV delta T plus nR delta T. We take n delta T as common, we get CV plus R, which is nothing but NCP delta T. And this is the total heat supplied in the isobaric process. So in this lecture, basically we learned two new processes. That were, the first was isochoric process, in which the volume is constant, and we try to find what is the work done and what two cases that can be possible. That is, under the isochoric process, either the heat is applied to the system or heat is taken out of the system. In that case, the temperature raises, and then the heat is taken out of the system, the temperature of the system decreases. Under the isobaric process, the pressure is constant in the process. So what all the three terms have the same sign in it. So if heat is supplied to the system, the delta T is positive, that is the temperature increases, and the work done by the gas as well as the internal energy is positive. And if heat is taken out of the system, all the three terms are negative. Okay. Then we learned basically the work done by all these processes. That requires a bit of work. We have to just try and express the terms in terms of each other such that the integral is valuable, and we can make the use of the first law of thermodynamics and delta U being the state function in order to simplify these calculations. And sometimes we don't even need to calculate anything. We can directly put the value of delta U, etc. So that's all for today. Thank you.